Hi everyone, good morning. So I'll be presenting this journal paper, which wasn't presented in a conference yet. So I apologize in advance for some duplication from yesterday's talk. This is for the sake of self-completeness of the. So we're talking about multi-agent planning, and this is the right track. We have several agents that are now cooperative, that can act and affect this the system and each other, and we're looking for a coordinated plan as a solution. And the example I like giving is logistics. We have trucks and airplanes, which are the agents. They move packages around, affecting one another. The motivation here and the reason that we're not using a single agent planners or classical planners in this case is that because we have private information that the agents don't want to share, and centralized planners require full knowledge of the problem. So once we talk about privacy, it leads us right away to distributed problem solving. These agents are going to solve this problem in a distributed fashion, each having an abstract view of the system. The main challenges we tried to tackle when we started this work is first, scalability. So the existing approaches, they worked well on loosely coupled problems where coordination between agents was, let's say, not so complex. But once the number of agents rises or the coordination becomes more complex, these problems are just not solved. And the other challenge is finding a way to solve these problems to find cost-optimal solutions to these problems. And the approaches which existed before only found locally optimal or suboptimal solutions. So we seek to minimize the cost of the plan. The main contribution of this work is a general schema for privacy-preserving distributed forward search to solve this multi-agent planning problem. And we show two instantiations of this schema. Both are scalable and one is cost optimal. And as a little added bonus, we found a pruning technique which is applicable also in single agent planning. So the model is multi-agent strips due to Brafman and Domschlag, 2008. And essentially, it's a regular strips problem where the agents are assigned actions. So each action is assigned to exactly one agent, and everything else is the same. Actions are given by their preconditions, effects, and costs. So this is classical planning, just partitioning the actions between agents. So the issue of privacy and how we define it is a key issue here. And once we partition the actions between agents, this induces a distinction between public and private actions, where public actions affect or are affected by more than one agent, and private actions affect only the agent performing them. In the logistics domain, move actions are private since they only change the location of the agent performing them, and load and unload actions are usually public because they can achieve or destroy preconditions of other agents' load and unload actions. So given this notion and this distinction between public and private actions, we took the existing benchmarks, single agent benchmarks, and we made them into privacy-preserving problems by considering all private actions as private information which the agents don't want to share. So in a sense, each agent has an abstract view of the system, and no single agent holds the entire problem structure. So how did we go about solving this problem? We went for heuristic forward search. Statespace forward search is found under the hood of most, let's say, state-of-the-art planners, and we said, why not bring it to distributed search and privacy-preserving search as well? So in the centralized case, we maintain a single search space. We start with the initial state. We expand states using actions, and we choose the best state that we see as the next state to expand, and stop when a solution is found. The main challenge here is choosing the best state, and we use complicated heuristics to do this. But that's the basic schema for this solution. Now, to take it to a distributed version, we make some minor changes. First, we don't hold a single search space. We separate the search space, one for each agent. In these individual search spaces, the agents expand nodes using only their own operators or actions, and nodes that are relevant to other agents are sent via messages. And the key observation here is that since we have private actions which do not affect other agents, if we have a state that's the result of a private action, this does not change any other agent's view of the system. So we don't need to communicate these states. We only need to communicate states which are the product of public actions. And I'll go quickly to show you this example. On the left-hand side, you have the action graph. Yellow means private action, red means public action, and the edges correspond to dependencies of these actions. In the middle, you can see the reachable search space, and on the right-hand side, you can see the distributed search space, one for each agent. So, as I said, they start with the initial state, both agents, they start expanding, and the first thing that we can see is that we reach, agent 2 reaches a state where in the reachable search space, there are applicable actions for that state, but both these actions are actions of agent 1. So agent 2 does not have any applicable action to perform here, and this essentially becomes a dead-end state for that agent. Agent 1 continues expanding using its own private actions until it applies a public action, resulting in that red state, which is then communicated to agent 2, and agent 2 goes on to expand states using its own private actions, reaching the goal. Again, in this example, it's a simple example. We only show one-way communication, but the algorithm does two-way communication. States go back and forth, and that's okay. It's still complete. So let me discuss the experimental results and some preliminaries. I'll tell you what I compare to. At the time of when we wrote this paper, there were two methods for distributed search. One was planning first. It's a paper from 2010, which uses distributed CSP to take care of the public part of the problem, and local planning to take care of the private part. And we also compared to MapPop by Ronen et al., which searches in plan space, and it builds upon the partial order planning paradigm. And it aims to solve, it was created in order to solve more tightly coupled problems than planning first. So let's talk about the experimental results. This is for the logistics domain, which is an inherently tightly coupled domain. Not many private actions, most actions are public. And we see three metrics here. First, the solution cost, then runtime, and then messages. Let's start with solution cost. The first thing that you can see, and as I said, this is tightly coupled problems. Planning first, that column of X's, did not solve any of these problems. MapPop was successful in solving most of them. And the solution cost is, let's say, comparable to the solution cost of multi-agent forward search. For runtime, I think this is orders of magnitude speed up over MapPop, and it's completely dominant over all these problems, and in message complexity as well. Just one word about the messages. These are very small messages. They consist of states. So that's the size of the message, linear in the number of variables. And these are the results for a more loosely coupled domain. It's satellites. And again, we can see that in terms of solution cost, the two methods, map-pop and multi-agent forward search, are comparable. But in terms of runtime, multi-agent forward search outperforms these other two existing methods, and in terms of messages as well. Just one thing about scalability, because this was one of our main efforts going forward. We ran these problems on a multi-core machine, trying to scale up to as many as 40, around 50 agents. And we're comparing here to fast downward, which uses exactly the same heuristic estimates. And this is for logistics. We see that the problems are solved faster, but there is some, the hidden variable here is the number of cores that is being used. So for multi-agent forward search, we use a core for each agent. So we see a better runtime, but you should actually multiply this by the number of agents. So the efficiency here is sublinear. This is for the that was for logistics, a tightly coupled problem, and for the more loosely coupled problems, there's actually superlinear efficiency here. So there's superlinear speedup, and I'll say a few words about how we can get this superlinear speedup. Okay, so the other challenge was to come up with cost optimal search for this privacy preserving problem, and in the centralized part, in centralized methods for cost optimal forward search, we need to have an admissible heuristic, and once we take this into account and take the G, which is the distance from the initial state to the state that we're estimating, once we choose to expand a goal state, this means we have found a solution to the problem. In the distributed case, this is not true. So we still do need an admissible heuristic, but expanding a goal state is not enough. We need to perform a distributed termination detection procedure, and we need to check essentially if the value of that state is lower than or equal to the global f value, the global minimal f value of the system. And we use the snapshot algorithm by Chandy and Lamport to do this. Very quickly over the empirical results. What I'm comparing to is a centralized A star implementation on top of fast downward, and maybe I'll talk, because I don't have too much time, I'll talk about the rightmost column here. This column is here to demonstrate the differences in heuristic accuracy. So we have private information. No single agent knows the entire problem structure, and this means that their heuristic estimates are less accurate than the heuristic estimates in a centralized problem. And to demonstrate this, you can see the heuristic estimate for the initial state. This is an average value over all the agents, but you can see that since this is an admissible heuristic, A star would always have a better heuristic estimate, so this leads to a more accurate search. I'm not going to have time to discuss the other stuff. Maybe just one thing. So for the loosely coupled problems of rovers and satellites, you can see the efficiency column. So this is the speed up divided by the number of cores that are used. And a number that's above 1 means that we did a more efficient search than centralized A star. And this is only due to the fact that we're pruning some of the states in the search space. As in my example, there was this orange state that we pruned. So 1 minute? 2 minutes. Okay, I'll skip the scalability results, but we're not so good when it's tightly coupled, better when it's loosely coupled. Also in the paper, in the journal paper, you can find our result about this pruning that is an inherent quality of this distributed search. But we also showed how to use this in single agent search, and we showed how to. So this pruning is essentially because we have a partitioning of the actions and we have private actions. So we said, why not create these private actions in single agent search as well? How do we do that? We need to decompose the problem, and we showed how to decompose the problem automatically and use this pruning rule to reduce the number of states in the search space. So to quickly sum up, at least at the time when this paper was written, this was the state of the art for privacy-preserving multi-agent planning. And MAD-A star, which is the cost-optimal version of this, was the first such algorithm that solves cost-optimal privacy-preserving planning. And but this may not be true after the planning competition, or the multi-agent planning competition. One more thing is that we provide this code. It's implemented on top of Fast Downward. It's open source, and you can all use it. I hope you enjoy using it. Thank you.